Why don't we go ahead and get started? So welcome everyone to today's analog work group meeting. And Mehdi, it's glad to see that you're on. I know you've been traveling and whatnot, and also Mohammed, that you can make it too, and everyone else too. So there are three different things we're going to cover today. And the first thing, Jean-Paul is joining us to present about Coriolis, or if I'm saying that correctly. And I think that might be of interest to folks. So Jean-Paul, why don't we start with you?
Thank you. And hello, everybody. So I will talk about the analog capabilities of Coriolis, which are linked to the digital one, because our focus in extending Coriolis to the analog world was to make something to really unify the design, to make really to really make mixed design. So not in the right. Okay, so this software is done by the science team of the Sorbonne University. We have a lot of experience in making analog design, and especially because we are in close contact with the teams that makes analog design. So it's easy for us to discuss about what they see as constraints or problematic things when they do their design. And one thing that I did learn in discussing with analog designer is that they are very sensitive. They have a way of doing things, and they usually do not rely or do not easily rely on automated tools. So the main focus of Coriolis is not to target full automation, but to automate what must be automated and let the analog designer make his choices when he sees fit. So it's guided automation, I would say. And we want to register the experience of the analog designer more than to force him to use a specified guidelines. So before I dive into the analog the analog itself, the analog part itself, I will just make a quick reminder of what it is to perform a digital place and route. In the digital world, what you have is standard cells, like those little you can see on the left-hand side of the screen. Then you put them inside rows, regular rows, and you put it according to a lot of criterions to minimize the wire lengths and many other parameters. But basically, this is what we do. So here we see the placed design with a lot of free space, but it's for the show. And the last step is to perform the routing. So the routing entails to dividing the routing is divided in two stages: the global routing and the detailed routing. And this is done around, this articulates around the GCells. What you see here, there is a close view on the left of one GCell, and a GCell is just an abstraction of a small part of the design, because the design is too complex usually to manage directly. So we perform global routing, which is routing over the GCells only. We consider only the GCell as one point of the grid. And then we perform the detailed routing, which amount to following the routing decided at the global stage, choosing the right tracks to put really the wires. This is when we do the wire. So this is what we do in the digital world, and it's articulated around GCell. So GCell is an important concept that we will extend for the analog designs. So now, the analog flow that we use in Coriolis, that is not exactly that we use, but this is how Coriolis should be integrated inside a complete analog design flow. What we do is that first there is the stage of sizing, when you decide the size of your components according to frequencies and all the analog constraints that you want to realize. Mainly, it boils down to defining the placement and defining the width and length of your transistor, the size of your capacitors or resistor. Then you perform a place and route, which gives you a GDS file, a layout. And from that layout, you extract parasitics. Because due to the placement, you have to take into account parasitics made by wires or folded transistor on a lot of things. Then what you do is, do you, with the parasitics, which is the real design, do you match your I don't remember the word, the requirement. Are you matching the requirement, or are the features okay? If not, you resize your design knowing the parasitics. That is, you inject inside the sizing, the sizing step, the parasitics. And the idea of this loop is that save for the first iteration, the modification would be small. So the PNR will just make small amount of adjustments. This is the implicit hypothesis that we work on. In the next, I will focus only on the blue part, which is made by Coriolis. So when we have an analog design, it is built upon devices, unless digital design, which are built upon standard cells and macro blocks. In analog design, we use devices which have the particularity to be sizable. Meaning, for example, in case of a transistor, it is a one finger transistor, you may want to fold it, and that is to build the whole transistor from multiple smaller ones. Because usually in analog design, you may have very wide transistor in electrical term, very wide. It's here, it's the 8 in our case, but very wide transistor that may use up a lot of space and may be very difficult to place efficiently if you don't fold them. So you can fold your transistor. Here, it is not folded. In the second stage, 2 folds and 4 folds. That gives a form factor function. That is, you have a lot of possibilities for one device, and this goes for the resistor, for the capacitor, and for other kind of devices. And we get some kind of a function which is convex, which is important to make the placement. So we have here the convex function of this transistor. The second step is to assemble those devices, those atomic elements, inside a placement. There are a lot of ways to assemble them, but for the sake of simplicity, we choose an H tree. No, not an H tree, a slicing tree. In Coriolis, in the analog part, we assemble our analog device into a slicing tree. Yes, a slicing tree. And you can see here at first level, it's an horizontal node. I mean, maybe the tree is not that easy to see, but the first level is with the long red bar, the black bar here. So we have 1, 2, 3, and 4 horizontal blocks. Then at the second level, we have vertical block. Here we have D1 and D2, which form one horizontal block, then D3, then D4, D5, and D6, which also compose another block. So this is how we assemble our devices. Then with those devices, we can also apply symmetric constraints. For example, here we said that D1 and D11 must be symmetrical. Same goes for D2 or D10, D3 or D12. This is a classical constraint in analog design to have symmetric devices. And some part of the tree may be symmetric, but not all of them. For example, D15 is not symmetric with anything, or D13 or D14 are not. The next step, after applying the symmetries or defining the symmetries, is to transform our design into an array of GCells, or it's not a matrix in that case, it's just a partition of the space using GCells. And how do we do that? First, as you must be aware, you do not place routing wire above the devices. That is, D7 area, D2 area, D1 area are forbidden for wire. The consequence is that you use a channel routing approach, meaning that everywhere that you have a separation given by the slicing tree, you get a channel. So here we have a vertical channel, another vertical channel, and a third vertical channel. In the same way, you have horizontal channel there, vertical channel here. So we create the channel, and in addition to the channels, we also have struts. Struts are, in fact, steel boxes, but to pad the devices that are too small for the area. It often occurs in analog design that one device is too small to completely fit, to completely fill the area into which it is assigned. So to manage that free space, we create special boxes which are called struts. So here we have two struts on top and bottom, and two struts on left and right to center the D3 device. All those boxes are then converted into GCells, but with different properties. And for the router, that will come afterward, struts are slightly different properties and will be handled different than channel routing. So finally, what we got is this. This is the final GCell partition representing the analog design. And on top of this tree, we can then also define symmetric constraints. For example, here, we said that this net, the blue one, is self-symmetric, meaning it will be routed symmetrically regarding to this axis, the axis going through D7, the center of D7. And this is one net which will be symmetrically routed. Of course, it must go only through symmetric part of the design. If the design is not symmetric itself, you cannot route symmetrically a net. In the same way, you can also symmetrize two different nets. For example, the net on the left will be symmetrical to the net on the right. And you just have to tell the router that you want symmetric parts. So now, how does works the devices generator? What we have implemented in Coriolis is a Python generator which generates the layout on the fly. So we have a basic part, a common part, which is in C++, and which generate what is invariant, that is the netlist of the transistor. For example, whatever the layout, it will always be a transistor with a source, a drain, a gate, drain, source, and a bulk, and with some electrical characteristic like the width, the length, and many other parameters. On the other hand, the layout has to be customized for every technology. So to do that more easily, we use a Python generator. That is the layout part is delegated to a script that you can customize. And we made a script to generate any kind of folded transistors. And we generate not only the layout, but also the form function. That is, here you have the 3 points of the form function, and there can be many others. And when we want to work quickly, we only generate that form function for the placer to estimate the area of the design. and only when we are satisfied, we just really generate the whole layout. And this script is completely parameterizable through the technology. That is, once we have decided how we want to draw our transistor, we just have to inject the specific parameter of the technology to get a DRC clean layout for that technology. So that's quite supple. Besides, our generators are not only basic transistor generator. In our case, there is often in analog design, you have pair rate transistors. And because in reality, in this drawing, in this schematic, the two transistors are clearly separated. But in reality, their fingers are always interleaved to maximize the pairing and compensate for all the defects of the substrates. So we have a lot, we have currently 8 constructs of interleaved transistor, and the generator can automatically create all of them. So it's the building block, because it's those parts are the building block of analog design, usually, plus capacitor and resistor, of course. So here is an example of such a device. So if I recall, you can see on the outside the guard ring. We have a guard ring. You can make it or not, it's optional. On the leftmost side and rightmost side, you have dummy transistors. You can see that their gates are connected to the source and drain. It is also, if I remember correctly, it is a source bulk connected. And it is, I don't remember exactly, it is a common source montage. There are 2 transistors here, 2 transistors interleave. And the interleaving is just ensured by here how you connect to the different drains. We have 2 drains here, and we can choose, it's easy to choose to which drain we connect. And by changing that, we can completely change the functionality of the device. So this is the layout that we choose to implement. But if you change the script, you can change completely that shape. So now, the maybe most interesting point of Coriolis is how he managed mixed design. You see here the regular grid for the digital part, and mixed with this regular grid, there is the irregular grid, or just a space partition of the analog part. And the interesting thing is that it is working on the same data structure. For the global router or the detailed router, there is no difference. It is an unified data structure, which allows us to completely manage in a completely unified way the place and route of the mixed design. So this is what says that the schematic on the left side. Of course, digital placement and analog placement must stay separated, because they are clearly completely different algorithm and things. It's completely different. But once the placement is done, we get onto the global route and the detailed route, and those 2 steps are completely unified. It is the same global router which performs the analog routing and the digital routing. And it is the same router which performs the detailed route for both analog and digital part. So what feature are we supporting now? Now we support only transistors. We have all the sockets ready for capacitor and resistors, but unfortunately, we have not been able to find internship, or at least we find internship, but the result was poor, so we didn't integrate it until now. But everything is in place to use capacitor or resistors inside the script. And now I propose you to illustrate that presentation with a small demonstration. We use a GM, Shamla, as I am from the digital world. I am not exactly sure what a GM is. It's, I think, the first stage of a differential amplifier, but maybe that's not the point here. The point is to see the logiciel work, the software work. So I hope it's not too teeny here. So I will just run the software, TGT. So all these are Python scripts. So I will just run the Python script generating the design. So it's called GM. And you see the design. I will try to make it a little bit bigger. So this is the design after global route. We perform the placement and we perform the global route. What is interesting is, for example, to see the GCell matrix. So here I will erase all the layers and only display the GCell level. So here you see the GCells. So you see the channels here, the device, and a lot of device, and that should be not a channel, but a struts here. So you can see the design. I will redisplay everything, erase the GCell, so we can see a little bit more clearly. Sorry, I will also erase the edges, and now it's cleaner. So what we have here, now we can perform the detailed routing. As I said, the global routing has already been done, and we can perform the detailed route. So detailed route. And here, the detailed routing has been performed. Now I will try to show you symmetrical nets. So it's a little bit crowded to really display everything. So we have the netlist. We can synchronize the netlist, and we see the nets. It's VB4, VB5. Where are the VB? Okay. VB7. Okay, and VB5. So, for example, VB7 and VB5 are self-symmetric nets. That is, from the vertical axis going through the center of the design, you see that the net have been routed symmetrically. And for VB7 is even more clearer, it's just a straight line. So no problem with that. Then we can also see different nets, symmetrical. So the AMPP 73, it's the 73. AMPP 73, where is it? Which one? Okay, this one. I will perform a cumulative selection to see both nets, and it's the 72. So if you can see here, the left side is symmetrical to the right side. And moreover, we can also adjust the whole design. For example, here, we can select the slicing tree curve. It is all the possible shapes that we have for the design. We compute all those shapes with the form function of each device and build all those points by aggregating them using the slicing tree. So we can choose this point, or this point, or this one. So the idea is to allow the designer to easily choose which shape he sees fits. The bottom line is here in green is the Pareto front. That is here, it's not an optimal solution, of course, but here we have optimal solution, and you can again reroute, perform a detailed route. So we see that things are a little bit complex. I don't know which one got selected. It keeps one net selected. And to illustrate the mixed design capabilities, I will now run another example, which is a little bit more complex. So GM prog. I think it's GM decode. GM decode. Here it is. So here is the design. And as before, I will show the GCell grid, which is interesting. So I remove everything but the GCells. And what you can see here is that the digital part is using the digital router with the regular matrix grid, while all the rest of the design still use a partition of the space. And then we can perform, I will re-apply everything. And use the slicing tree. The slicing tree is very simple. The curve is very simple due to the digital blocks, which makes it's not deformable. It has been built as a fixed size block, but that can be improved. So we can use one here and perform the routing. The decoder it's a programmable decoder, and you see everything has been routed correctly. So this is the end of my demonstration. I hope you liked it. So I did finish. It was a bit longer than expected, but I hope you enjoyed it.
No,
thank you for your...
No, thank you very much. It was very informative, and I sincerely appreciate you taking the time to come to us today and share this with us. Are there questions from the audience, from folks?
So sorry, please continue.
This is Steve.
Hey, Steve, you're breaking up.
Breaking up?
You were. Try again.
Can you hear me now? Okay.
Yes.
Okay. I like your slicing floor planning stuff. Is there some way early at the placement stage to also get a wire length metric or something like that in order to determine whether you have a good placement without having to run the simulation itself? It's just being compact doesn't necessarily mean that the wires are short.
It's very, as the global router and the detailed router are very fast. It's easy to run them and just extract the wire length. So you can have that quite quickly. I don't mean an extraction. I just mean running the placer and router, and the router in that case, even only the global router, because the detailed routing will follow very closely the global routing. So you can have quickly an estimate of the wire length.
And then how do you what you think is the best placement ahead of time, right? Do you that's not what you do in your flow now? I mean, we would have that graph, right? You have width versus height. We would have area versus wire length on that, on a graph, and then we would choose which placement we like based on being Pareto in that space.
Yes, that could be done. It's not very complicated to implement.
Okay.
Hey, Jean-Paul, your audio dropped down again. Are you using a directional microphone?
No, I am using the microphone of my laptop.
Oh, okay. There, you're back. You're back.
Maybe just try to cancel the noise a little bit to badly.
That's right.
So
Other questions?
Yes, this is Thomas from Infineon. Unfortunately, I missed the first 10 minutes of the presentation. Maybe there this was already covered, but your placement, let's say, your placement algorithm, I think in this, let's say, in this example that you showed right at the end now, is there some possibility to say, okay, you want to compact it more? Because when I looked there at this layout, there was a lot of space there. I don't know, maybe it was linked to some constraints in your example, or can you run some, let's say, some additional algorithm there to compact the different transistor placement in the analog part more? Or?
I think this is the work of the analog designer to choose is a slicing floor plan. This is where we left the analog designer to choose it. I think, yes, it's not, it may be not efficient, but in that case, it's the meaning is that the designer should have to change the the slicing tree.
Okay, I see. So in your example, you defined the slicing tree in that way, and that was then the reason why it looked like how it looked like.
Yes.
Okay, I see.
You just change the slicing tree if you want a better fit to the size of your component, and you will be more compact.
Okay, but the slicing tree you still need to do, let's say, manual. So there's
Yes.
no way to say now try to find some optimum for the slicing tree. Not yet.
No, not yet.
Okay, understood. Thanks.
Script quickly, you can change it quite quickly.
Okay. Yep. Thanks.
Any other questions from folks?
Yeah, hi, this is Boris Merman. One quick question. The layout you showed, it looks like it's all minimal routes, minimum width wires with one contact. How do you deal with higher current densities and IR drops and things like that? Or wider traces, right, if the designer needs them?
We can handle non-default wires, non-default width wire. Of course, yes, in this example, I only used minimal width wire, but we have support for non-minimal width wire.
So the designer specifies this for each net, or how is it handled?
Yes, it can specify it for, it has to specify it for each net if he wants a non-default width.
Okay, thank you.
Other questions?
Hey, Jean-Paul, I had a question. So I'm wondering what technologies are you supporting and which tape outs have you done using this tool?
We have not done any tape out using this tool yet.
Because is there any plan to support SkyWater 130 or any other technology?
Yes. Now that you are all aware of the NDA problems, and as we wanted to perform free and open source tools, we were always limited by that. So I think we did support 350 nanometer from AMS. We did have a check with that. Otherwise, it's not very complex to support the technology. We have to just to enter the design rule inside some kind like a spreadsheet, and everything configure almost automatically. But yes,
so
we did not.
I'll just add that Chipflow has done tape outs on the digital side with SkyWater 130, and that was in I think 4 or 5 that went in on.
So wait, you guys taped out something in SkyWater 130? That's what you're saying, Rob?
Yeah.
Okay.
Yeah, the digital side.
On the digital side, okay. So is this tool open source? Are we able to go play with it?
So
yes.
even the demonstration I showed you are completely open source. In fact, they are based on the SCMOS 180 nanometers from Moses. So it was configured for that. It's the dimension of the transistor are completely wrong, I think, because they were calculated for another technology. But the point was just to show something that works. Once you configure things correctly, the results are correct.
I think Rob put in a link to the open source repository. Rob, maybe you could repost it. I seem to have lost it here on my side. I'll put it in the minutes.
Yeah, sure. Let me
Sorry
just
about
paste
that.
it again. No worries.
You have two repositories. You have the one for the tool itself, Coriolis, and you have the one for the examples, which are shipped in another repository, which is Alliance Check Toolkit.
Yeah, I've just given the top level link there, Jean-Paul, to coriolis.lip6.fr.
I had a software question, Jean-Paul. I'm just curious, is this built upon, what type of data representation is this built upon? Is it, obviously we all know about open access and some of the challenges relative to that from SI2/Cadence. Is it using that, or is it using your own representation that you've built, or something else?
We use our own representation. We use the Hurricane database, which is packaged with Coriolis, and which is a kind of an alternative to open access. It has a similar functionality features.
What was it called again? What was it called again?
Hurricane.
Oh, Hurricane.
But
Okay, got it.
It is shipped with Coriolis. It's an integral part of Coriolis.
Understand.
So,
It was.
Yeah, go ahead. Sorry.
Sorry, no, I just wanted to add that it was developed by a company which is Bull, the Bull company, French manufacturer of PC, Bull.
Okay.
Bull in English.
Mehdi, did you have a question?
Yeah, so I was wondering, if you bring in a new design, how does it come with a constraint file like a line, or do you have to write? How does it work?
You have to write a Python script describing your design, and in doing so, you can add the constraint you want.
All right. Well, how do you write the Python script, right? How do you describe your design?
It's not very complex. Maybe if my screen is still shared, I can show you. It's gm.py. So what we have, okay, you have to design your transistor, then the netlist itself. It's a work in progress. I think it can be much improved, but it is working. And what you had here is, where does it done? Yes. You have add symmetry for, it's for those symmetries are for the nets. No, those for the GCells, to say which GCell are symmetric, and for the nets, I don't remember where the symmetry of the nets are defined. Okay, add symmetry net. You just have here to just give the nets you want to be symmetric. So here the self-symmetric nets, and if you specify two nets, you give paired symmetric nets. But all this is Python scripting over the C++ interface. If you want to change that interface because it doesn't suit you, you can completely overwrite it. This is, I would say, it is a first attempt, and we can completely rewrite it to any other syntax you see fit.
Well, it looks promising. Just that, when the design gets a little massive, it becomes a little tricky, right?
Yes, but I think it's completely configurable. If you want to import it from another format, or you have all the power of Python to do whatever you want.
Okay. I
must say that this is a 4-year-old work. that is, we had a PhD to perform to the extension, but since then the work has stalled because we don't have enough resource to develop it. Should we have it, we will be much further advanced.
Appreciate that. Is most of the work done by university students?
Yes, but a PhD, yes.
Yep, I understand. Okay, it's about 20 minutes to the hour, so maybe we finish up on Coriolis, Jean-Paul, and thank you so much for taking the time to come present to us again today, and I'll make the recording of this available too for folks. Thanks. Mehdi, should we switch to you? Did you want to update on the PMU work?
So I didn't necessarily prepare slides. I just have a couple of screenshots. We kind of
Okay.
swamped by the tape out. It's on the 9th, so just a couple of days from now.
That's fine.
Yeah, so update on that. We have a floor plan of the PMU. GDS factory is working. We're able to generate the flying caps and all. And it's DRC and LBS clean. The only issue we have is simulation. We have run the simulation over 2 days now and still running in GSpice. So I think there's an issue with larger design when you run a large simulation with text extraction. But this is the top right now. We're trying to figure out a way of doing some connections like the comparator and noise injection block. But yeah, that's the overall status right now. So you're just trying to close this as soon as possible.
And this is going to be on a one of the Skywater eFabless shuttles?
Yes, correct. So this is going to be integrated with the Open Titan core. And I'll try to make some slides after the tape out, which are going to be much clearer than this, but just wanted to give an update on the tape out and maybe branch out on the possible, silicon area we have for next shuttles. We brought out last week, Rob.
Yeah, we definitely have opportunity for shuttle space, thanks to Mohammed and eFabless that we could take advantage of. So I think it would be great if we could have a project that would leverage that.
Yes. So Maddie, just in case it doesn't make it for the lottery reason on the Google Shuttle, we're gonna commit a chip ignite slot for it. Okay.
Oh, thanks, Mohammed.
Yeah. It's because I just want to be clear. eFabless's interest in this is to encourage the development of relevant IP functions that are to be open source, and then make it available in a complete way that are reusable. So eventually we need to, we were talking about the standards with the community, etc. But we have an open call is that, if the certain IPs that would be included in a useful chip. When I say useful chip, it has, it's a complete, it have analog digital power management, etc. We want to do this, so that's our incentive, just so you, and it's aligned with what the community wants. And it could happen by itself organically with the Google shuttles, but it's not. We want to accelerate it.
That makes sense.
Sure.
No, thank you for that, Mohammed. I appreciate that.
Everyone that's doing the real work.
What's that?
Thanks to everyone that's doing the real work.
No. Okay. Any other comments, Mehdi?
Yeah, I was just wondering if Jean-Paul or Rob would be interested in taping out something using Coriolis for analog design, since we have area, I guess, this time.
I think it's definitely of interest. Yeah, be interesting to see what people think would be a good thing to tape out.
What's the timeline on that, Mehdi?
Well, I don't know. It all depends on Jean-Paul, I guess, who's developing the tool. So it would be a good demonstrator for their tool, right? It's always
Absolutely.
good to make a tool, but then you have to demonstrate it.
Happy to make a design, but I have to be. I am the tool maker, so I need a design to work on.
I see. Well, maybe you can use your tool for one of the designs here in Chips Alliance.
Yes, absolutely no problem with that.
Yeah, are you gonna be in the Free Silicon conference in France?
Although we initiated it, I will be in vacation at the time. It's silly timing because they decided the date after I make my reservation. So it's completely stupid. I won't be there.
That's the best project type. You initiate it, let everybody come in and do it, do the overwork and then engage, and then you'll go have vacation. Anyways, thank you.
Yeah, anyway, so thanks, Mehdi, for that, and Jean-Paul. So I think if we could get an example, then with Coriolis, that would be wonderful.
Yeah, I have a couple ideas. Would be great to meet again, Jean-Paul, and talk about that if that's possible, or do it in a different Chips Alliance meeting. But it would be great to try the tool and see if it is as promising as it sounds like, right?
Some refining, but all the bases are there.
Mm-hmm. Great. So maybe I'll follow up through emails and see.
I think everybody has my email. No.
I think I do. Feel free to share.
Yeah. I can put it in the minutes. I think you cut out there, Jean-Paul.
Yes, what? Sorry.
That's okay. I will put your email in the minutes, as I said.
Okay.
So, Mehdi, anything else from your side?
No, that's all. I mean, it's the tape out week, right? So
Right.
it's
Okay.
really,
Got it.
Yep.
So just other two quick updates from my side. We are looking at trying to pull together a website, not only for the Analog Work Group, but also for Chips Alliance in general. Chips Alliance does have a website. It's WordPress based, which for those that are familiar with that particular product, it's not necessarily what I would say is engineering friendly. So we did meet with the Open Power folks, and we in general like what they have in their venue. We don't necessarily need all of the bells and whistles, but it is effectively Git based and is constructed via Hugo. So it may be something that we look at, or we are looking at to use for re-architecting the CHIPS website, and then also making it more friendly for the developer community.
So regarding that, Rob, last week I met with the OpenRoad team, and they have made this website which looks really cool. I was thinking maybe that could be an option.
Sure.
And we do have, I mean, they know the people who developed that, so maybe you can see how we can get that done the same way.
That would be great. Yeah, no, I'm very open to different ideas, because as we're really still exploring. The main thing that I know is that we need to do something different than what we have.
Sure. I think we should reach out to, I think Andrew is here, but Tom or Indira would be the good people.
Okay. Then the one other item I wanted to update on was that CHIPS is looking at having a kiosk at the Design Automation Conference here. I think it's the second or third week of July, as part of the RISC-V Pavilion for the open source effort. And so I don't know if anyone would be interested in helping participate at the booth. If so, just drop me an email. But looking at that, and I will be there myself on Monday, July the 11th. So for those that will be in the Bay Area at that time, hope to see you in person.
You're there
So-
all week, just not one
Go
day.
ahead. What's that, Steve?
Will you be there all week or just?
No, just one, no, just that one day because I have my son's wedding that later that week that I have to help out on, obviously. So I'm just the one day.
Yeah, I can help one of the days, Rob, as I told you.
Okay.
Yep.
I will send, I have a spreadsheet with time slots, so I will fill that to you, send that to you.
Awesome.
I appreciate that. Is there any other topics that folks want to cover today?
Congratulations. In order.
Oh, thank you. All right, if there's nothing else, then we will call it a wrap for today. Oh, I just saw your thing here, Andrew. Okay.
I will be there.
Yeah, that's great. I'll put that in the minutes too. All right, thank you everyone for your time today. I appreciate it.
Hey, Rob.
Thank you all.
Thanks. Bye-bye.
Yeah, Manny.
Yeah, I'm just gonna ask Rob, since I have him here. Are you gonna able to send the slides?
I'll try my best. I think it's going to be the best I can do at this point. But
Well, I
will
think,
try.
I mean, you probably have the material. You just need to make a video. It's really
Yeah.
important, right?
Yeah. Really, I really want to do it. Just like I say, I've been ill, and the children have been ill as well. So it's just been pretty difficult. But I'll see what I can do.
Isn't that recorded or as well?
Sorry?
The session was recorded as well, right?
Yes.
Yes. All right.
Yep.
Well, thanks everyone.
All right.
Thanks, Rob.
Thanks, guys. Bye-bye.
Thanks. See you later. Bye.